All right, here I'm going to be talking about some compound probability, which basically just means that we have more than one event. So simple probability is just one thing happening. Compound probability is, let's say, rolling a die and flipping a coin, or flipping a coin twice. More than one thing is happening. And that splits into two different categories: independent probability and dependent probability. Independent is the simpler one. It's when the two different events, or more than two events even, do not affect each other. So let's say I'm rolling a die. That's my best die that I could draw, and flipping a coin. Those two do not affect each other at all. Whatever I get on the die, let's say I roll a 1 on the die, it doesn't somehow change the probability of getting a heads on the coin. Those are independent events. They don't affect each other. Dependent events would be, let's say I have a bag of Skittles, and I have some red ones, and I have some green ones, and I have some blue ones. And let's say I take one of those Skittles out. Let's say I take out a red one and I eat it. The bag is now different from what it was before. That's what it means to be dependent. The situation changes after the first thing happens. I have this bag with 3 red Skittles in it, and now I eat one of those. Now I only have 2 red Skittles, and I also only have 7 Skittles altogether. I had 8, now I only have 7. So the situation changes as you go from the first event to the second event. That's what it means for them to be dependent. The second event is dependent on what happens in the first event. So anytime you're dealing with a spinner, it's going to be independent events because the spinner doesn't somehow change in between the first spin and the second spin. So here we're talking about what's the probability of spinning an odd number and then spinning a red number. So we want to think about these two separate events. The first event is getting an odd number. There are 1, 2, 3, 4 odd numbers out of a total of 8. The chance that I get an odd number is 4 out of 8, or I'm going to simplify that into 1 out of 2. The chance that I get a red, that's my second event. So I'm spinning it a second time. I'm basically ignoring what happened on the first one because this second spin doesn't somehow change based on what happened in the first one. Oops, I'm highlighting that in red, sorry. That 7 is the only red number. So there is a 1 out of 8 chance that I get a red number when I spin this. When you're talking about two events, you're always talking about the probability of the first one times the probability of the second one. The chance that we get an odd number times the chance that we get a red number. So I'm gonna multiply those two probabilities together. 1/2 times 1/8. When you multiply fractions, you multiply straight across. 1 times 1 equals 1. 2 times 8 is 16. So the chance that I get an odd number is 1 out of 2. The chance that I get a red is 1 out of 8. The chance that I get an odd number and then spin it a second time and get a red is 1 out of 16. Same spinner. Probability of spinning a yellow number, oops, I missed a word in there, 3 times in a row. What's the chance that on the first spin, I get a yellow? On the second spin, I get a yellow. And then on third spin, I get another yellow. So again, these are independent events. The chance that I get the first yellow doesn't change the second one or the third one. They're all separate events. So I'm thinking about yellow number as these two options. 2 out of the total, which is 8. I'm going to simplify that into 1/4. So the chance that I get a yellow on just one spin is 1/4. Then I'm going to spin it again. It's going to be the same thing. It's going to be 1/4 again. And then 1/4 again. It's 2 out of 8 for each of these spins because this spin doesn't somehow determine what's going to happen in that spin. These are independent events. And now I'm going to multiply straight across. 1 times 1 times 1 is 1. 4 times 4 times 4 is 64. So the chance that I get one yellow spin is 1/4. The chance that it happens 3 times in a row is 1 out of 64. What's the probability of rolling a 2 on the die? There are 6 options on a normal die, and then flipping a heads on the coin. So I want to know the chance that I get a 2, and then on a coin, there's really just heads and tails. So this has a 2, that has a 1 out of 6 chance. There's just 1 2 on there. That has a 1 out of 6 chance. Getting a heads is a 1 out of 2 chance. To find the chance that I roll a 2 and then get a heads, it's 1/6 times 1/2, which is 1 times 1 on top, which is 1, and 6 times 2, which is 12 on the bottom. I have a 1 out of 12 chance of getting a 2 and then a heads. What's the probability of rolling a number greater than 2 and then flipping a heads? Well, I just talked about that. Chance of getting a heads does not change. It never changes, actually. It doesn't matter if you flip a coin 10 times in a row and you get heads. That 11th flip is still 1 out of 2. That's a common misconception, especially in gamblers, that they think that somehow the odds are in their favor because they haven't been able to win in the past. That is not true at all. The odds of flipping a coin never change. It's still 1 out of 2. I'm going to list these out again. 2, 3, 4, 5, 6. Those are all the options on a coin. The ones that are greater than 2 are 3, 4, 5, and 6, which is 4 out of the 6 options. I'm going to simplify that into 2 out of 3. I'm dividing by 2 on top and dividing by 2 on the bottom. 2 out of 3 times 1 out of 2. That's the chance that we get a heads. You multiply straight across, and you get a 2 on the top and a 6 on the bottom. So usually when you simplify these in the beginning, not usually, some of the time, when you simplify these in the beginning, you might not have to simplify this, but sometimes you do. When this and this have a common factor, you are able to simplify that, and here we simplify by 2, and our final answer is 1/3. So we have a 1/3 chance of getting a number that's greater than 2, and then getting a heads. Those were all independent probabilities. A coin and a die and a spinner, the odds don't change from one event to the next. When you're dealing with a bag of M&Ms, if you take out an M&M and you eat that M&M, the bag is changed in between the first event and the second event. You really have to read carefully for this phrase. Are you replacing it or are you not replacing it? So here we're looking at the probability that we get a blue M&M, we replace it, and get another blue M&M. If you're replacing that M&M, we're taking out one of these, putting it right back in, we're back to the original bag. These are actually independent events, because we replaced it. We reset the bag to the original probability. So the chance that we get a blue, we want to think about the blue out of the total, which is 3 out of, there are 6 groups of 3, so 3 out of 18. So the chance that we get a blue is really 1 out of 6. Then we put that blue right back in. So the chance that we get the first blue is 1 out of 6. The chance that we get the second blue is also 1 out of 6. The bag is completely reset, so the probability of that second event does not change. I'm going to multiply straight across on top. 1 times 1. Straight across on the bottom. 6 times 6. That's 36. That's the chance that we get 2 blues in a row. The next problem, the only thing that I'm going to change here, I'm still choosing a blue, then choosing another blue. The only thing that I'm changing is that I'm eating it in between these 2 events. So the first one, that doesn't change. That's still 3 out of 18 or 1 out of 6. The second one does change. I'm assuming that this actually happened. I picked out a blue and I ate it. There is less blues in here now. I ate one of those blue M&Ms. So my second one might be a little bit different than my first one. Actually, it will be different. I'm thinking about now, what's the probability in this new bag that I get a blue? Well, I'm still thinking about probability as favorable outcomes over the total. So here I have 1, 2 blue M&Ms left, and I ate one of the M&Ms. So instead of having 18 there, now I only have 17. This goes down to 2. This goes down to 17 because I ate one of the blue M&Ms in here. And again, to find the probability of two different events, you're still multiplying straight across on top and on bottom. That's going to give us 2 over 6 times 17 is 102. This actually does simplify. Those are both even numbers, so I'm going to divide by 2 on top and by 2 on the bottom. And that means I have a 1 out of 51 chance of having that happen twice in a row if I eat the first blue one. And that should kind of make sense. Just judging, like comparing these two answers, that is a higher probability. 1 out of 36 is a higher probability than 1 out of 51. Because I didn't eat that blue in between, I lowered the probability of getting a blue one on that second random choosing. These are dependent events. Dependent. Because this probability is impacted by that probability. This second random choosing is dependent on the first random choosing. All right, same bag of M&Ms. What's the probability of randomly choosing a blue or a red, replacing it, and then choosing a blue? So on that first one, let's go with green because that's not red or blue. We are looking at getting a blue or a red. So I can get any of those. So that is 6 out of the 18 options. Then for the second one, I want to get a blue one. Now think about this again. I replaced that one. So I took out one of these. It doesn't matter whether it was blue or red, but I put it right back in. So I'm back to the original bag. I don't want to even think about what happened in the first one because this is the original bag now. Now I'm thinking about what's the chance that I get a blue. That is 3 out of 18, just like before. Let's simplify each of these. That turns into 1/3. That turns into 1/6, and I can multiply straight across. 1 times 1 is still just 1. 3 times 6 is 18. So that's the chance that I get a blue or a red with the first event. And then the second event, after replacing that blue or red, I get a blue one. So those are, actually just to make it clear, those are independent events because I replaced the first M&M. What's the probability of randomly choosing a blue or red M&M, eating it, and then choosing another blue or red M&M? So I'm thinking about the first one. What's the chance that I get a blue or a red? Still, just like before, we're in the original bag. That is 6 out of 18 options. And now I'm eating that one. Doesn't matter whether it's blue or red. Let's say it was a red one. Let's say I ate a red one. Now on that second random choosing, I have 1, 2, 3, 4, 5 out of, I ate one of these 18 M&Ms, so now I have 17. You could see that even if I pretended it was a blue, it doesn't really change anything. Thinking about blue or red, I still have 1, 2, 3, 4, 5 out of, I had 18, I ate one of them, now I have 17. It's still 5 out of 17. Actually, before multiplying, let's simplify this. That's 1/3 times 5 out of 17, which is 5 out of 51. When you see the phrase without replacement or eating it or putting it aside in any way, we're not replacing or changing the second event or the third event or the fourth event, whatever it happens to be. These are dependent events, because the second event is dependent on whatever happened with the first event. We're going to go over one more problem, and we're looking at, actually this problem is very similar to one on your scavenger hunt for this week. What's the probability of picking all 4 kings without replacing each card? That immediately tells me these are dependent events. It tells me that after I pick out 1 king, I'm not going to have the same deck of cards that I had to start out with. So I'm looking at this set of cards. What's the chance that I pick out one of these kings? So these are my kings. That is my first king. That is a chance of 4 out of 12 options. Now on the second one, I'm not replacing that one. It doesn't matter really which one I pick out. I'm going to say it's this one. Now I have 3 kings left, 1, 2, 3, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cards altogether. And you should see clearly what's happening there. I'm losing a king, going down from 4 to 3, and I'm losing a card, going down from 12 to 11. Let's say I picked out that one. So that was the second king I picked out. Now I'm picking out the third one. And you can see that it doesn't actually matter which order I pick them in. That's kind of important. The order doesn't actually matter. It just matters that I'm picking out a king the next time. So on my third one, I now have 2 kings left. And I'm also losing a card. I have 8 here, 9, 10 cards altogether. Let's say I took out this one. Now on my fourth one, I only have 1 king left. And I only have 9 cards left. I have the 1 king and these 8 jacks and queens. I'm still thinking about the probability of all of these happening. It means I multiply those probabilities together. I multiply that, times that, times that, times that. I definitely want to simplify these first, especially these two. That turns into 1/3. That one turns into, sorry about that arrow, that turns into 1/5. 1/9 doesn't simplify. So now I can multiply those probabilities together. Something that you might catch on to, if you have a 3 here and a 3 there, you know that once you multiply these together, you're also going to be able to simplify by 3. I'm going to show the whole process, but you might be able to pick up on this where you can actually cancel out these 3's before multiplying. But I'm just going to multiply straight across. 1 times 3 times 1 times 1 is 3. That was supposed to be a 3. And 3 times 11 times 5 times 9 is 1,465. So like I said, if you see a common factor here and here, you know that you're going to be able to divide on top and bottom by that common factor. So I'm going to divide by 3 on the top and 3 on the bottom, and that would give me a final answer of 1 out of 495. So that's the probability that in this just set of 12 cards, that I pick out a king, a king, a king, and then a 4th king before I pick out any other cards.